Welcome. As always, I interpret the given problem. I'm looking at a rectangular channel. The channel is 1.2 meters wide. The goal is the discharge. The vertical depth, this dimension, 1 meter. The velocity profile is specified. Coordinate y is measured from the wall. The angle is 30 degrees. Next, I want to connect this problem to what I already know. I see water running down a slope under the influence of gravity. Oh, this is like water running down a street during a rainstorm. Because of the no-slip condition, there is a velocity profile. The given problem simply involves a lot more water than what I would see running down the street. Rectangular channel means that if I were to look across this section, so I cut across there, and I look in this direction, I would see a rectangular channel. The shape looks like this. This dimension is 1.2 meters, and the height h is less than 1 meter. This equation is a big problem because it's not dh. Let's fix this problem. dh, or dimensional homogeneity, means that each term in an equation has the same dimensions or the same units. Here's the problem. This term has dimensions of length per time. This term has dimensions of length to the 1/3 power. These are not the same dimensions. Let's fix this problem. So here's how I fixed it. I wrote the velocity profile like this, where u max is the velocity at the free surface right along there. Y is the distance from the wall, and h is the height measured in this direction. To use this equation, I need to find the value of u max and the value of h. To find h, I made this sketch and then wrote this equation. Here's the value of h. To find u max, I wrote the original velocity equation, then I substituted numbers in. Here's how that goes. Here's the first step. I put in the value of h max, and here's the value of the maximum velocity. Summary. I started with the given velocity profile. I rewrote the equation like this, solved for the two constants. The resulting equation is dimensionally homogeneous. Yay! The advantage is that when I use this mathematically, I can carry and cancel units and then check my results. Finding a solution path for this problem is straightforward. Here's why. The problem involves a velocity profile. When I see this, I know I can integrate the velocity profile to find flow rate. Here is the equation I will use. Let's get started with the problem solution. I summarize the given information with my situation diagram. I write down my goal. To find my goal, I select the flow rate equation because my goal appears in this equation and because I know the velocity profile. Next, I need to find the differential area. Since the differential area is a rectangle, I multiply the height of the rectangle, dy, by the width of the rectangle, w, and here's my formula for dA. So next, I'll take my equation for velocity profile and substitute it in there, and I'll take my equation for differential area and substitute it in there. Let me do this and rewrite my expression. Here's my integral after I've cleaned it up. Let me do term-by-term analysis. There's the goal. U max is known. The height of the channel is known. W is known. Y is a variable of integration, as is dy, and the limits of integration are both known. Therefore, I have one equation and one unknown. I can go ahead and solve this equation. Step 1, I'll take all constants and pull them out of the integral. So this is constant and it can come out, this is constant, it can come out, and the width is also constant, it can come out. After I rewrite the equation, here's what I get. So now I need to integrate y to the 1/3 power. After integration, here is my result. Let me go ahead and apply the limits of integration for this expression. Here's what I get. Now I'll combine this term and this term, and here's an equation for the discharge given in terms of variables. Next, let me substitute numbers into this equation. This shows my calculations, and the final answer is given right here. The discharge is about 3/4 of a cubic meter per second. Review comment number 1. I try to write equations so that they are dimensionally homogeneous. DH is a simple idea. All terms have the same dimensions, or another way to say the same thing is all terms in the equation have the same units. When I know a velocity profile and my goal is to find discharge, I know that my solution path will involve integrating the velocity profile over area, and I use this idea all the time. This concludes the example. I hope you found this super useful. We'll see you next time, and thank you for listening.